Right, Jim, you can take it from here.
Sure. Yeah, and just a note, right? You're welcome to speak up and ask questions out loud or type them into a chat. But yeah, since we are recording, if you speak up, just be aware your voice will be part of the recording, but no names are going to be released. So you're welcome to participate. It'd be great if we can participate. The goal of this session is it's ask an expert. There's a few of us on the line here that have all been using Intel FPGA AI Suite. We support it on the Intel side, and we'd love to have interaction and have you interrupt us and ask us questions as we go through this. So some introductions. This is myself. My name is Jim Mowat. I'm a technical solutions specialist. Part of the Programmable Solutions Group, the FPGA and EASIC division at Intel. I'm focused on AI, IoT, and edge compute applications. And you can see a little bit of my background there. I spent several years in design a long time ago and have been working for the past roughly 15 years in various support roles working with customers. A lot of that has been focused on FPGAs. I guess I'll let Kevin introduce himself.
Hi, everyone. My name is Kevin Drake. I'm an AI software solutions engineer here at Intel Corporation. I have a bachelor's degree in computer science from Sonoma State University. I work with AI Inference using FPGA AI Suite. I'm also involved in the Intel FPGA University program, and I was a former member of the U.S. Air Force. Thank you.
And Domi as well.
Hello, I'm Domi Papoy. I'm also AI software solutions engineer at Intel Corporation in San Jose. I specialize in AI software development at Intel and work with multiple companies like Qualcomm, AMD. And I have a master's in applied science, focusing on HCI. And that would be like, I speak multiple languages for that.
Yeah, great.
Right.
You all met Rama earlier. Yeah, go ahead, Rama.
Yeah, myself, I work in software marketing, FPGA AI. I just want to let you know there's two ways to ask your questions. You can ask by voice, you just unmute, or you can ask by chat. And I will bring it up to the presenters as they are presenting. Okay, thanks.
Yeah, so I guess some ground rules here as we go through this. I'm going to talk a little bit about what the FPGA AI Suite is. But as you listen, then after that, there'll be tons of time for Q&A. Any question you have about the AI Suite, this Intel FPGA AI Suite, it's fair game. Feel free to ask us. If you have like a detailed design specific question, feel free to ask, I suppose. But if it gets to be a little bit too deep or too specific to your design, right, then we may end up asking you to take that offline, right? Unless it's something we can answer in a reasonable amount of time, great, we'll answer it here. And if it really does need a lot of deep follow-up, we're happy to connect you with whoever the local field application engineer is to help support you further. Okay. So why you're here, maybe you're asking questions like, what is Intel's FPGA AI tool? Or something like, how can I quickly implement AI in an FPGA? Maybe you're an FPGA engineer and you're asking, how do you integrate AI stuff into Quartus, the Quartus Prime software? Or maybe it's the opposite. Maybe you're a software engineer and you work with an FPGA team. How can you, as a software engineer, maybe doing some data science work or algorithm work, how can you contribute to FPGA design? How do you get from TensorFlow or PyTorch or Onyx, get some kind of deep learning model that you've worked with in one of those frameworks into an FPGA design? You might have any one of these questions. Hopefully those are some of the reasons why you might be here. I don't know if you've got other reasons, but if so, feel free to let us know. And this site here is the landing page. We should probably make sure to paste it in chat because I don't think you'll be able to click on the screen, but that's the landing page for FPGA AI Suite. And from there, you can find various information. There's a link to browse documentation and so on. I'll go ahead and put that in chat. Okay, so I'm going to start here by talking a little bit, just a few slides here on a high-level overview of what FPGA AI Suite is, and then after that, Kevin and Domi also have a few things they're going to show you guys, just a little bit hands-on to demonstrate a couple simple things with the tool so you can see it a little bit, and feel free to ask questions. Okay. So a few definitions. Right? The name of the tool, Intel FPGA AI Suite. Right. AI, artificial intelligence. What do we mean by that? Well, I mean, a broad definition of artificial intelligence is really any technique where computers are mimicking human intelligence. There's actually nothing new about this. There have been algorithms, from basic decision trees that go back to the 1960s and 70s, and if it's mimicking human decision making, that can be considered artificial intelligence. Over time, that's developed into machine learning algorithms, and usually we think of some of these things as, a lot of times people say classic machine learning, which is really any algorithm where machines are able to learn and improve from data. You feed it some data. There's algorithms like, k-means and various other algorithms like that we might categorize as classic machine learning. And then in recent years, there's been a lot of development into deep learning. This is what we call like a subset of machine learning, where you're using deep layered, that's where the word deep is coming from, neural networks, where you feed in a bunch of data to get it to converge on an algorithm, a deep learning model that can do something useful. Okay. More specific to that, one category of deep learning models is convolutional neural networks. These are convolutional in nature. They tend to do really well. They're suited for things like 2D spatial data, imaging type tasks. They can be used for other tasks too, but we're specifically pointing out convolutional neural networks here because that's really the focus of the Intel FPGA AI Suite. Okay. So its main focus, the thing that this tool suite does, is it allows you to crunch on convolutional neural networks in an FPGA. With that, just one thing to note, maybe this is obvious, maybe not, but various deep learning algorithms tend to be a lot more compute intensive than some of the more classic machine learning type algorithms that existed and that still exist and that are still useful. But if there's a deep learning algorithm that can do a task well, great. But then there's always this question of, okay, it's a lot more compute here and a lot more data it's crunching on. How do we make that work well? So that's something to keep in mind, and it's something that's useful in the context of FPGA, because FPGA, we do have a fair amount of resources that can really help us crunch on deep learning algorithms. And so to be a little bit more clear, I talked about convolutional neural networks, some other big picture categories of deep learning neural networks. There's convolutional neural networks. There's something we call multi-layer perceptron neural networks. These are things like your recommender systems, like your algorithms that are suggesting what the next advertisement should be or what the next thing you want to watch, the next video you want to watch is. Those are typically MLP algorithms. There's also a variety of recurrent neural networks, things that are often used for speech and natural language processing. When you think about language and natural language algorithms, looking at the past few words, the history of what's happened in the past, helps predict what's about to come next. So, in addition to what it's hearing, right, it looks at the history of what's happened. These are often very recurrent in nature. And so just to point out what we have today with the Intel FPGA AI Suite, it supports convolutional neural networks, as well as it can support MLPs as well. Today, this tool suite doesn't support recurrent neural networks. If that's something that's of interest, let us know. We do have other options for how to crunch on recurrent neural network algorithms, things like partners that have developed their own engines and IP blocks and so on. Another thing to keep in mind when it comes to deep learning, there's the training side of deep learning, which the training side is where you take a bunch of labeled data. In this example here, where we've got a bunch of images of humans, bicycles, and cars. right? Different humans, different bicycles, different cars from different angles and different lighting, each labeled as, is it a human, is it a bicycle, is it a car? And we can push that through a deep learning neural network. In our case here, it'll be a convolutional neural network. And, as you feed the data through, this process of training will change the weights and adjust the weights and figure out, okay, this picture I just got, was it a car? No, it wasn't. I was wrong, right? And it'll adjust the weights and say that it was an error. And you keep converging until you do have a model where it does quite well and can properly differentiate as the weights converge on a model that will differentiate between the different things in your data set. Okay, that's the training side. Once your model is all set, it is properly doing this task, differentiating between humans, bicycles, and cars. Now you want to run it in a device. You want an actual thing that's going to do this. It's going to identify between humans, bicycles, and cars, or classify waveforms, or whatever your task is that you need to do. Find defects, whatever it might be. That task of actually running in the device is what we call inference. And so that's where you just feed it the data. It runs the algorithm based on the weights that you came out of the training side of things and tells you the result. That inference side is what we're deploying in the product, and that's what we're doing here with the Intel FPGA AI Suite. Okay, and some examples of these inferencing tasks are things, when it comes to imaging, it's things like image classification, like we were just describing a second ago there, humans, bicycles, and cars, or person, sheep, dog. Similarly, we have object detection. The detection is, not only finding those things, but putting bounding boxes around them. A more specific version of detection is really where we do segmentation pixel by pixel, figuring out which pixels are associated with the object you found. All these are various tasks, and these can all be accomplished by convolutional neural networks. And so really we can support these kinds of tasks in FPGA using the Intel FPGA AI Suite. So I don't know if there's any questions at that point. That's kind of a big picture overview. The next portion here, I'm just going to talk a little bit about why FPGA. Well, there's a few reasons here. These are some big picture reasons why FPGA is useful in general, and this is specifically applies to AI just as well as other applications. But FPGA, you got a blank chip, you can program it, you can do whatever you want with it, and being able to reprogram and change what the circuitry and the hardware makeup of the chip is can really help. If there's new deep learning models that keep coming out, which this is a very, very fast moving field, we can change up the IP block, this engine in the FPGA that crunches on those AI models, to be able to do a better job with new models that might have a different structure and might make better use of a new engine that operates in a slightly different way. We can adjust and adapt as time moves forward. Right? We don't have fixed silicon where we can't adjust the way it is without spinning a brand new chip or a new device to do that. Okay. And actually, something that goes along with that is these are device families that we support with the FPGA AI Suite. It's really all of our families that are supported in Quartus Pro. So Cyclone 10 GX, Aria 10, Stratix 10, Agilex 7, and the upcoming Agilex 5. We've already seen a really useful aspect, which is customers that are already using our FPGAs and have been in deployed products and want to add AI into them. Maybe you want to add AI into your existing FPGA design. You can do that because the device is programmable, and you can take an IP block that is generated and include it in an existing design. So again, it's one of the nice things with FPGAs. If you want to add a new feature into something that you've already deployed, you can do that. It's part of this ability to react to evolving markets and changing needs out there. And obviously, as an FPGA, usually there's some reason you're using an FPGA, which is there's some custom hardware that is useful to your system. Now you can include with your custom hardware AI as well, right there in the same system. Also, given that we have an engine that's basically operating as a hardware assist inside the FPGA, you've got this hardware-based engine to crunch on deep learning models. That means that it really ends up being very low latency in terms of all that compute. I talked about how deep learning models, it's a lot of compute. but we can do that compute in a parallel fashion in the FPGA and have it crunch on things in a really short time. So if there's applications where every microsecond starts to matter and you need really real-time AI, we can do that. So for those familiar with FPGAs, you know what the things are made up of. If there's any on here that aren't necessarily FPGA users, it's a blank chip, but it's built up with a few building blocks. You have just general logic. So we call these logic elements, or sometimes the term LUT is used, lookup table, because it's a LUT-based logic. Or sometimes in documentation, we'll call them adaptive logic modules. But whatever it is, right, there's whatever you want to call it. There's this sea of logic, and interspersed within that logic is memory blocks. Most of our devices these days, the memory blocks are little 20K SRAMs. Okay, so there's a lot of these 20K SRAMs throughout the die. They're represented in this drawing here by these colorful stripes. The blue stripes are memory blocks. The orange stripes are DSP blocks. So that's the other thing that's sprinkled throughout the logic is these DSP blocks that can do multiplies, little multiply accumulate units. And you have lots of them, hundreds and thousands of them, depending on the specific FPGA. So there's a lot of capability to do multiplies. And when we look at deep learning models, deep learning algorithms, you have convolutions, those are multiplies. You need logic, all right, to build up an engine, and you need places to buffer the data that's flowing through. And we've got all the building blocks in the FPGA. We have logic, memory blocks, and mults, and actually they all marry up really well to be a really great hardware platform to build up an engine to crunch on deep learning models. So that's a big part of what we've done here is we've built up an IP block, an FPGA IP block, an engine that can crunch on deep learning. We often use the acronym. If you start to dig down and install our tools, you'll see this acronym DLA or CDLA, C for core, it's an IP core. DLA stands for Deep Learning Accelerator. So that's the IP block that comes along with the FPGA AI Suite. Okay, it's actually generated for you. It's generated based on how much FPGA resources you want, right? You can size it up to be a more performant IP block that takes up more resources, or you can squeeze it down to be a smaller IP block that takes up less resources. It's tuned to be specific to a deep learning model that you provide if you'd like, or multiple models if you like. And so you get this IP block that's been parameterized and tuned to how you want it. It works a lot like other IP blocks we generate. Whether it's FFP IP blocks, or we have a tool that ties in with MATLAB DSP Builder. Those tools kind of generate a chunk of IP, and the same way FPGA AI Suite will generate a chunk of IP, and now you can include it in an FPGA design. And so these are a few pictures of how you might use an FPGA with the FPGA AI Suite to do useful things that include AI. And this first one on the left here, most of our FPGAs have an option to have an SoC version of the chip that has an ARM processor system that can run an operating system like Linux. And so now you've got a nice host environment right there within the FPGA where you have Linux running on an ARM CPU, and then you can include all your FPGA things. And that's really nice because you can have a standalone system. A lot of customers deploy products today that are an embedded SoC FPGA where there's an ARM host that can do all kinds of things. In terms of deep learning, that's great. We can have the ARM host be the host that kind of kicks off and starts the inference and sets up doing this deep learning inference, and then include that in with other things you're doing in your FPGA already. And this is a great way to make use of an FPGA. And we say plus AI. Do the existing things you're doing in an FPGA plus AI as well, right there in that same FPGA. Number two here is really very, very similar. But maybe you have an external host that is going to be receiving results of your inference and maybe coordinating and kicking off things and runs a whole big software solution and the rest of your application on top of there. Okay. The big value here in these, number one, number two, is FPGAs are really good at aggregating and collecting tons of data. We have lots of I/O. We support a wide variety of flexible, really high-speed protocols. And so that's where FPGAs are often used. They're pulling in lots and lots of data in many applications already. And rather than just ship the data off somewhere else and then do AI elsewhere, it can be really useful to do it right there in the FPGA where the data is already. Number 3 and number 4 are a little bit different. It's the opposite side. This is where the host CPU is kind of the center of the system, and data would be flowing in and out of the FPGA through some interface from the host to the FPGA, typically PCIe. And you could fill up the FPGA and purely use it as a CPU offload where it's just doing that deep learning acceleration. Or of course, it's an FPGA. You can put other things in there if you'd like and do other hardware functions just as well.
Hey, Jim, there's a question in the chat.
Yeah, I see that here. Comparison to CPU-based products, i.e. ARM, speed, and overhead. So I'm going to assume, feel free to correct me if I'm assuming wrong. I'm going to assume you're asking, how does running inference in an FPGA compare to running inference on a CPU like an ARM CPU? Yeah, I got a thumbs up there. Of course, CPUs can do deep learning inference, right? They can do compute, they have multiply accumulate blocks, but when you think about like the multiply resources in the ALU of a CPU, there's only so much it can do at once, and you end up having to crunch on it in a serial fashion. When we build up this IP, this BLA IP, we've got a big parallel compute block doing lots of multiply accumulates all at once. So it will crunch on and do all of that in less clock cycles. And on top of that, we're not tying up the CPU that you probably need to do other tasks. So it's a trade-off of how you want to do things, performance you can get, time to get an inference result. All those things will be improved by putting it into an FPGA IP block as opposed to trying to run it on a CPU. Yeah. And I haven't talked too much about how things flow in to this, from a software standpoint. There's this logo here, OpenVINO. OpenVINO is an open source project that Intel's been behind. Maybe you've heard of it. It's been around for 5+ years. And it's used quite a bit to run deep learning inference on CPUs, whether it's Intel CPUs or given that it's an open source project, it's being used on ARM CPUs as well. OpenVINO lets you take a deep learning model from, at this point, really any of the industry standard frameworks, PyTorch, Keras, TensorFlow. It brings in ONNX format. And so you can bring in a model and run it. And in the case of CPU, the idea is to get that deep learning model to run as efficiently as possible on the CPU. From an Intel CPU standpoint, we like this because we can make sure it's that when you run inference, you're leveraging all the things on the Intel CPU. If we've got special instruction sets, VNNI instruction sets, AMX extensions, instruction set like AVX 512, whatever it is that might be there in the CPU to do that. If you've got great resources in the CPU to do that, OpenVINO, for CPU, will make sure that you can run as efficiently as possible on the CPU. The other thing OpenVINO supports is, instead of running inference on the CPU, pushing that inference into what we call like an accelerator. And that's exactly what we're doing here. We're using OpenVINO and telling it, don't run inference on the CPU, run it on the FPGA. Yet another thing OpenVINO supports, which is really, really nice sometimes, is it can do heterogeneous compute where it runs on both the CPU and something else. CPU plus GPU, CPU plus FPGA. And so we can push and run inference in the FPGA. You could also run inference such that maybe most of your inference runs in the FPGA, but part of it runs on the CPU. So a deep learning model can get split across multiple devices as well using OpenVINO. That's one of the advantages of using this OpenVINO framework as the way we deploy the inference. Happy to take more questions. That was some of the things I was going to show from a slide standpoint here to kind of describe what's going on. I believe Kevin, I think, is next. He was going to show and talk about an example design.
Hello, everyone. Yes, I'm going to talk about the Intel FPGA AI Suite SoC design example. This demo will show an example of using an Intel FPGA AI Suite and an ARIA 10 SoC development kit. We're going to be doing the streaming to memory variant of the SoC design example build. It'll build on top of the memory to memory design to demonstrate a method of using AI Suite with a continuous streaming input data. The application example is typical video stream being processed with ResNet 50 to detect physical objects in the images, such as a person, cat, or dog. In the example, test images are stored on the SD card file system. These images are loaded into host memory, and a DMA memory to streaming IP is used to create a simulated video stream. Some of the images on the screen here are examples of images that could have been used, and a sample of the model is included on the right. Give me a moment here. So as you can see on my screen, the left side is the ARIA 10. We are SSH'd into the ARIA 10 in 2 separate sessions. The first window will run the image stream, and the second window will run the inference stream. So as you can see, it is outputting the, probably hard to see from there, it is outputting the identification and the score for the object detection. Also, if you look on the right side of the screen, you will see that I have Ubuntu 20 running in a WSL2 environment. This is simulating a 8-core laptop with 32 gigs of RAM. First, I'm going to run the OpenVINO benchmark app, which will show the throughput for ResNet 50 on a simulated CPU. And then above, I'm going to show the DLA compiler showing us the throughput on the Agilix 7. So if we just give those a moment to finish. As you can see, it shows that the subgraph was split into 1, so this will be entirely on the FPGA. Are there any questions so far? Looks like we have one in the chat.
Yeah, there's a question in the chat about, can you share technical references, manuals, white paper, etc. I sent a link to the main page. It's got documentation. There's 6 documents and an app note there. In a second, I'll also paste in a solution brief white paper that is available as well.
Thank you.
If you're looking for something else that you don't see there, let us know.
Okay, as we can see, the throughput for the CPU was quite lower than some of my other tests because I'm running so much stuff in the background. But we're looking at about 11.5 frames per second versus the FPGA, which shows 146 frames per second. So you can see the FPGA does provide quite an acceleration boost. And that's the end of my demo. Are there any questions?
Thanks, Kevin. I had one question. Maybe it's for both Jim and Kevin. Is there, how do you run different kinds of graphs? If I want to remove a layer on ResNet, does the tool flow allow us to do it?
OpenVINO does have a tool that will allow you to cut the model into submodels. You can go into the source code for a model and swap out to another layer that we support. There are other caveats, like you'll have to look at retraining and accuracy and loss. But yeah, you can swap layers out to make your model supported.
Thanks.
So there's a question in the chat. It says, would you comment on Windows support from development environment to full system deployment? Right now, we support WSL2 on Windows, which you can use OpenVINO in our compiler. But when it comes to deployment on an FPGA, that is where a Linux environment as of now would be needed. Domi, do you have anything to add to that? Sorry, James, I didn't mean to interrupt you.
Yeah.
No,
the
Domi
Windows
probably knows
supports
more.
some work. Yeah.
Yeah, there is some work being done for Windows support if you need to deploy that. So if that's something you need, reach out to a contact, right? And we'll figure out if that's something we can support and how we can support it and in what time frame and so on.
Any more questions? I had one more question. So Jim, would you be able to comment on how a user can change the resources and trade off with respect to throughput? Maybe you covered some of it, but maybe you can touch on that.
Yeah, sure. I talked about it a little bit, but maybe there's a few other slides I could show that help describe it a little bit. I'm going to share something a little bit different here. So, yeah, I mean, you can size up and down the IP so that, it's building an engine that's going to be able to crunch on a deep learning model. And you can build that engine to be a large engine with a big, what we call PE array, processing element array, that's using up a lot of the DSP blocks in the FPGA. Or you can size it, down to be smaller, or you can even make it really, really, really tiny. And actually, something that maybe people don't always realize is just like other IP blocks, you can have different instantiations in your FPGA that are configured differently, sized differently, are tuned with different parameters, such that you now have multiple engines. Maybe one of them is doing a certain model, right, an object detection model, and maybe you also have a segmentation model running in the same FPGA, and they could run in different IP blocks, so they're not using the same resources, or they could run in the same resources. So there's a ton of options that can be done, and in terms of sizing up and changing up this IP block. I'm going to show you something that might appear a little bit scary at first, but this is what we call the .arch file. It's basically a parameterization file for that IP block, that deep learning accelerator engine. It's got all kinds of different things that you can adjust. And we know that if we hand off this .arch file to you as an end user, you probably look at it and go, I myself look at it and go like, I don't know what to adjust, and if I adjust, the K vector value here, how's that going to affect my performance of my deep learning model? We don't really expect the end user to make changes to this file much. We have instead generated a tool that will sweep parameters and make adjustments to these things for you. We kind of call that the architecture optimizer tool. Okay. So haven't really talked too much about the flow here, but the flow that we tend to have is we start with a trained model. Okay, so this is independent of anything that we are providing, right? You're working within one of the industry standard frameworks out there. TensorFlow is probably the most common, but many people are using PyTorch as well. And then you use the OpenVINO model optimizer. That gets it into a format we call IR. So this is like an OpenVINO specific format, this IR format. It's a little folder with an XML and a bin. And this is the starting point for what the Intel FPGA AI Suite uses. It's basically an add-on to the OpenVINO tool suite. And you've got to build up your FPGA hardware somewhere, and this is the starting point. And it takes a couple inputs, right? So one input is your model in the format of this IR data, right? This IR format of the model that comes out of the OpenVINO model optimizer. And then the second input that comes in is the number of FPGA resources that you're willing to provide to create an engine. So if you want to use up 80% of the DSP resources in your FPGA because you don't need them for anything else, great. You let the architecture optimizer use all 80% of those DSP blocks. If you don't want to use quite so many, you can size it down, right? Maybe you need them for other things in your design, or you're doing a bunch of fur filters or something like that. You also tell it how many how much of the logic, how many of the logic elements are ALMs, how many of those M20K type RAM blocks. You give those, that's the second piece of input. And the DLA compiler, it's a command line tool in Linux. You run DLA compiler and you tell it, generate a new architecture for me. So you give it a reference architecture and tell it to generate a new architecture. And this tool will basically take one of these .arch files and tweak and modify various parameters for your deep learning model, given the number of resources you told it could use. So you're not creating that whole big parameterization file. This tool will tweak and adjust it and generate it for you. And it predicts and shows you, an estimate of what kind of performance you'd be able to get. If you're happy with that, then you tell it, okay, go ahead and create the IP block. And then you get an IP block. And if anyone, those of you that are familiar with the Quartus tools in our platform designer, we have this format .qsys that platform designer uses. You can then connect it with other blocks using platform designer if you want, or you can just hook it up with regular RTL, Verilog, VHDL, and include it in your design. And we do have a couple example designs. I'm in the very first link I pasted into the chat with documentation. There's a PCI Express example design that runs on like a PCI Express card. There's also an SoC example design that Kevin was just showing us that runs on the ARIA 10 development SoC development kit. Those are two different example designs, but we have an example design where we've built up a whole Quartus project and have a way to execute the OpenVINO inference engine on the CPU and have it run inference into the FPGA. I know that was like a long explanation, but I figured that might have been the best way to really explain how do we support, sizing up and changing up the resources and the performance levels you get. I'll show a table here to just make that a little bit more clear. There's a lot of numbers here, but the idea here is in one of our like ARIA 10 FPGAs, this top line here, I mean, this is pretty small IP instantiation. So we've sized up that .arch file to be really small and compact so that the engine it builds is really pretty compact. It's using about 30 of the DSP blocks. An ARIA 10 device, the big ARIA 10 device here that we're talking about has well over 1,000 DSP blocks. So 31 is just a small fraction of what's there. And so with a small fraction of the device, we can get single digit number of inferences per second in terms of like ResNet 50 performance or MobileNet. Just a few rows down here, this isn't that much more logic. We're using a decent number of DSP blocks and a fair chunk of memory blocks. And now we've got many tens of of inferences per second in terms of performance. If you keep sizing it up, right, we can get hundreds of inferences per second, and we can put in multiple of these two IP blocks, 4 IP blocks, and really crank up the performance we can get. So you can scale up and down pretty easily, pretty well, and create an FPGA that has a lot of deep learning performance, or something that just has what you need depending on your needs. And so in that way, you want whatever you want, you can create.
Yeah, that's a great explanation, Jim. Thank you. There were a few more questions in the chat that we answered, but probably worth repeating. Are the resulting inference models from the FPGA AI Suite viewable, the ones that are generated in VHDL or Verilog? Yes, it is viewable. You will have to integrate that into Quartus using Platform Designer. Another question was, do we support low power devices such as Cyclone 5? We don't support Cyclone 5 right now. We support Cyclone 10, and we will continue to support future low power devices such as Agilex 5, for example, which is a great new product that is coming up for AI. And there was one more question on OpenVINO installation for FPGA. Is it included in the Quartus install, or should it be separate? So Quartus is a separate installation, separate from the FPGA AI Suite. You can run the FPGA AI Suite separately, explore trade-offs of, like Jim just explained, of trade-off of logic elements and DSP blocks and memory with respect to throughput before you get into quarters. Any other questions? Happy to answer. If not, we will close for this session. Thank you all so much for attending. We will definitely have future webinars, and we look forward to more engagement. And feel free to contact your Intel contact if you have any questions, further questions. We are happy to answer. Very quickly, we had a survey chat. If you could spend a few minutes responding to this survey, that would be great. I'm going to just post it in here and leave this on for a few minutes. So if you could please answer the survey, it would help us better plan for the product. Thank you.
Thanks, everyone.
Thanks, everyone.
There's a question on which version of Quartus is planned to support. So we continuously release with new versions of Quartus. So the most recent one is 23.2. The previous one was 23.1.
Yeah, and the documentation points out which versions of Quartus are supported. So I'm going off memory here, but currently I think we support any versions of Quartus from 19.2 up through 23. The latest 23.x, something along those lines. And there's yet another question here about, is a recording of this presentation going to be made available? Yes, this will be a recorded presentation. Attendees who didn't attend live can always come back and watch the recording.
Just a reminder for the survey link in case you haven't seen it. I think there's a question on a couple of FPGA families. Generally, yes, FPGA families are supported. As soon as we announce it, we typically we will follow with the support. But however, we don't usually comment on long-term projects. But generally, the plan is to support any new family, FPGA family with the FPGA AI Suite.
Yeah, and to be more specific, right, the question there has got some code names, but one of those code names refers to our Agilex 5 family, which is now public. And so FPGA AI Suite will be supporting Agilex 5. I think the release that will come out later this year as the Agilex 5 tools are becoming available will support targeting Agilex 5. Further out in time, as new families roll out, yeah, it'll support new families as well. The limitation right now, not that it's much of a limitation, but the limitation now is that the FPGA AI Suite is supported in Quartus Pro. So it supports the families that are supported by Quartus Pro. Quartus Standard and Lite, which are used for some of our older legacy families, like someone asked about Cyclone 5 earlier, does not have support for FPGA AI Suite. So as a result, currently we can't target Cyclone 5 with the FPGA AI Suite, but pretty much all the other families from the past 5+ years, Cyclone 10 GX, Aria 10, Stratix 10, Agilex 7, Agilex 5 as it's rolling out, and other Agilex families will all be supported by this tool suite. Yeah, great question. There's another question here. Where will the recording become available? And I actually do not know the answer to that.
It should be available on our web pages as usual. We will send out an email to those who have registered But you could generally, I can share a previous one. For example, our Signal Tap webinar, and it's under the category of developer on-demand webinars. So let me share that link. Any more questions? Please feel free to ask. Okay. Again, thank you all for attending. I'm going to stop the recording. And thanks again. See you next time.